At Rescue Education, we have the best explanation every time. I'm Dr. B, and I'm going to help you easily and rapidly learn organic chemistry. If you like this video, you'll love my self-help books. Learn more about them at rescueedu.com. Let's start our discussion of stereochemistry by talking about chirality, enantiomers, and chirality centers. First, we need to talk about the relationship of chirality and enantiomers. The concept of handedness permeates both the macroscopic and microscopic world. Hands are not identical. If you put one hand on top of another, barring some terrible genetic problem, your thumbs will point in opposite directions. We say hands are non-superimposable. Gloves also have handedness and only fit the hands they are intended for. Feet and shoes also have handedness, with a particular shoe easily fitting only one foot. Nuts and bolts must be of the same directionality. The entire body has this property of handedness, with the heart tipped to the left, the liver and the appendix to the right. The technical term for handedness is chirality. Chiral objects or molecules can exist as a pair of non-superimposable mirror images. We have already seen hands are non-superimposable. If you hold your hands with thumbs next to each other, you can see they are also mirror images. Enantiomers are two objects or molecules which are non-superimposable mirror images of each other. A pair of hands or a pair of gloves are enantiomers. Chiral objects or molecules can occur as a pair of enantiomers. Sometimes only one enantiomer of a chiral object will exist. Chiral molecules are very common. In biochemistry, chiral molecules usually only exist as one of the two enantiomeric forms. Chiral drugs are usually sold as one enantiomer. If they come from natural sources, they would only be made as one enantiomer. Synthetic drugs, that is, those made in labs, are usually sold as one enantiomer, but sometimes both enantiomers are sold together because it's cheaper to make the drugs as a pair of enantiomers. Enantiomeric molecules are extremely similar and have almost all the same physical properties. They have the same melting points, boiling points, and solubilities. Because of this, it is extremely difficult to separate enantiomers. But enantiomers differ in rotating plane polarized light in exactly equal but opposite directions. We'll discuss this concept, which is called optical rotation, in topic 5.3. Let's look at the two enantiomers of the simple chiral molecule 2-butanol. We will often use the convention of having a dotted line between two enantiomers to represent a mirror plane between the two mirror images. The left and right enantiomers both have identical boiling points of 99 degrees Celsius. But notice they have equal but opposite optical rotations of minus 13.5 degrees and plus 13.5 degrees respectively. Optical rotation is designated by an alpha in square brackets. The last thing I'll mention is that enantiomers will react the same with regular reagents. But they tend to react differently with chiral reagents like enzymes. It is likely one enantiomer of 2-butanol would react with an appropriate enzyme and one would not react at all. I highly recommend you build models of both enantiomers of a chiral molecule like 2-butanol. What you'll find is if you try to overlap them, two groups will always overlap and two groups will always be inverted. This is a characteristic of enantiomers. If we take the right-hand enantiomer of 2-butanol, we can hold the OH and rotate around the bottom to overlap the methyls with the left-hand enantiomer. What we see is that the methyls and hydroxyls overlap, but the ethyls and hydrogens are inverted. Enantiomers are a special type of isomer called a stereoisomer. You can go to topic 5.8 to see a table of all isomer types in organic chemistry. Stereoisomers, like all isomers, have the same molecular formula. Stereoisomers also have the same order of connectivity of atoms. But stereoisomers differ from each other by having a different arrangement of atoms in 3 dimensions. Enantiomers are one type of stereoisomer. Cis-trans isomers are another type of stereoisomer. Recall that cis-alkenes have groups on the same side of a double bond, and trans-alkenes have them on opposite sides. Next, we need to talk about the characteristics of chiral molecules and how to find chirality centers in organic molecules. A chiral organic molecule has 3 characteristics. First, it can exist as a pair of enantiomers. Second, it has at least one chirality center. And third, it does not have an internal plane of symmetry or any other symmetry element such as a point of symmetry. A chirality center is a carbon which has 4 different groups attached. You should be aware that there are similar names used in other books and by other professors, such as chiral center, stereogenic center, stereocenter, asymmetric carbon, or asymmetric center. We'll always use the term chirality center. In this generic example, you can see the groups W, X, Y, and Z attached to the chirality center. Chirality centers are indicated by a star. A molecule with one chirality center, such as this one, will always be chiral and can exist as a pair of enantiomers. Convince yourself that these 2 molecules are non-superimposable mirror images. Molecules with 2 or more chirality centers are almost always chiral. We'll talk about this in topic 5.4. An achiral, that is non-chiral molecule, has 3 characteristics. First, it doesn't usually have a chirality center. Second, it always has a plane, point, or other element of symmetry. And third, an achiral molecule is always superimposable on its mirror image. That is, they are identical. This generic molecule has 2 identical groups attached to the central carbon, so it has no chirality center and must be achiral. You can also tell this molecule is achiral because it has an internal plane of symmetry. If you rotate our original molecule so that the 2 Z groups are on the left and right, you can bisect the molecule with a mirror plane so that one half of the molecule reflects into the other. Atoms W, C, and X are bisected, and one Z reflects into the other. Finally, you can tell this molecule is achiral because it's superimposable on its mirror image. Convince yourself that these 2 molecules are identical by building models. To determine if a molecule is chiral, look for the presence of chirality centers. That is, look for carbons with 4 different groups attached. If a molecule has one chirality center, it must be chiral. If a molecule has several chirality centers, it is almost always chiral, and you can assume it is for this exercise. Remember that a chirality center is indicated by a star. To see all the chirality centers in the sugar glucose clearly, put in all the hydrogens so you can clearly see all 4 atoms attached to each carbon. When you do this, you see all the ring carbons are chirality centers. There are 5 of them. The CH2 on the left here has two hydrogens, so it's not a chirality center. Glucose has several chirality centers and is chiral. Pause and give these sample problems a try. Put a star beside each chirality center in the following molecules. Predict whether these molecules are chiral. First, let me point out that double bond carbons can never be chirality centers because they don't have 4 different groups attached. In the first molecule, dopa, which is an endogenous neurotransmitter, there is only 1 carbon with 4 groups attached. So dopa has only 1 chirality center, and dopa is chiral. The molecule carvone also has only 1 chirality center. It's at the bottom of the ring. Carvone is also chiral. It's interesting that one enantiomer of carvone has the flavor of caraway, and the other enantiomer has the flavor of spearmint. The final molecule is the ubiquitous steroid cholesterol. There are 8 chirality centers, and here they are. Convince yourself that all the other carbons are either in double bonds or have 2 identical groups attached. Cholesterol is chiral. Some other steroids you probably know about are testosterone and estrogen, which have similar structures and are actually derived from cholesterol in the body. Finally, we'll talk about manipulating the structures of chiral molecules. That is, moving them around in 3 dimensions. You may be able to skip this section for your particular class. Sometimes you need to compare drawings of 2 chiral molecules to see if they are identical or enantiomers. These 2 chiral molecules are obviously enantiomers. They are lined up so you can see that they are mirror images of each other. But sometimes the molecules are drawn in ways that are hard to compare. Manipulating molecules in 3 dimensions has other uses, but in this discussion we'll use it to see if 2 molecules are identical or enantiomers. Let's try to figure out if A and B are enantiomers or identical. We'll talk about 4 strategies to do this. Strategy 1 is to manipulate the molecules in your head. Obviously, don't try to do this literally. A small percentage of people can think so well in 3 dimensions that they can visualize how to move these molecules to compare if they are enantiomers or identical. This is a skill that can be learned with practice but may not be worth your time. Strategy 2 is to build models of each molecule and compare them. For many people, this is the best and most foolproof way. If you are allowed to use models on exams, you can build a simple model of each molecule which has a carbon with 4 different colored balls. Assign a color to each group. For example, a red ball is methyl, a blue ball is bromine. Build A and B and manually compare them. But let's say you can't do it in your head and don't have models. Then you can use strategy 3. Use the rule that switching 2 groups twice, that is a pair of switches, at a chirality center leads back to the original molecule. Let's manipulate B and see if we can overlap all the groups on A. If we can, then A and B are identical. If we can overlap 2 groups, but 2 are inverted, then A and B are enantiomers. We'll choose to switch the chlorine and methyl, and then we'll switch the bromine and the hydrogen. After 2 switches, we get back to the original molecule B. We compare A and B and see all groups can overlap, so A and B are identical. Pause and try this sample problem. Are the molecules A and C identical or enantiomers? Let's do a pair of switches on C. First, we'll switch the bromine and the methyl. It doesn't matter which two switches you do. Next, we'll switch the hydrogen and the chlorine. This gets you back to the original molecule C. What you can see is that the hydrogens overlap and the bromines overlap, but the methyl and the chlorine are inverted. That means that A and C are enantiomers of each other. Strategy 4 is useful when you have molecules drawn in completely different orientations. You can try to perform a series of what I call piano stool rotations to try to overlap the two molecules. You hold one group and spin the other three groups around. No bonds are broken, so you always have the original molecule, which is simply being flipped around. Let's use this method to compare A and D. If you hold the chlorine and D, you can rotate to move the positions of the bottom three groups. This lets you overlap the methyls and bromines of A and D. At this point, you can stop. While the methyls and bromines overlap, the chlorines and hydrogens are inverted. This means A and D are enantiomers. Convince yourself that any further or different rotations will still lead to two groups overlapping and two being inverted. You can choose any atom to hold. I happen to choose chlorine, but you can choose the methyl. There's nothing magical about what I did. Just a reminder that it's ideal if you can compare the two molecules in your head instead of using the other strategies. Pause and try this sample problem. Are the molecules A and E identical or enantiomers? While we can use any of the strategies, I hope you can see that all we need to do is to tip E to the left, and we get A exactly. So A and E are identical since all four groups overlap. If you're using my book, I encourage you to do the extra test your knowledge problems for this topic, so you can be sure you really understand it. All the answers are at the back. This video is closely based on my first semester organic chemistry self-help book. My self-help books are particularly valuable in difficult learning situations, but you can also use them to get an edge or to get a head start. If you want to learn more about my books and videos, how to get the books, or my future projects, go to rescueedu.com.